Hello everyone, welcome back. I am 𝑓𝑬𝑗yoti. This is For the Love of Physics. In today's video, I want to present to you the 5 postulates of quantum mechanics. Now, if you are a regular viewer of this channel, you must know that till now I have produced over 50 lectures on different topics in quantum mechanics, and only now I am presenting to you the postulates of quantum mechanics. Don't you think that's interesting or weird? Because we have studied so much about the subject of quantum mechanics, and only now we are going to discuss the proper postulates of the quantum mechanical theory. It's kind of interesting because so many of the ideas in quantum mechanics as a subject is kind of radical, non-commonsensical, that it takes some time for the student to get used to those ideas. We have discussed these ideas previously in different kinds of topics, but today I am going to give you a proper formal presentation of these ideas. Now, I want to read a line from this textbook, The Introduction to Quantum Mechanics by David J. Griffiths, the very first line. Unlike Newton's mechanics or Maxwell's electrodynamics or Einstein's relativity, quantum theory was not created or even definitely packaged by one individual, and it retains to this day some of the scars of its exhilarating and traumatic youth. So you must find it kind of interesting that whenever you study a different branch of physics, like if you study Newton's laws, you will be introduced to the, if you study mechanics, you will be introduced to the Newton's laws very early on. If you study thermodynamics, you will be introduced to the laws of thermodynamics very early on. If you study special theory of relativity, you will be introduced to the postulates of relativity very early on. But because of the nature of the subject of quantum mechanics, it has taken us so long to reach this particular stage. So it kind of makes me happy that we are kind of giving a formal introduction to the postulates of quantum mechanics. So the quantum mechanical theory itself is a hugely mathematical theory. The formalism is filled with mathematics. And there are two pillars of this mathematical formalism. One is the wave function solution or the quantum state of a system. The other is the operator associated with different physical quantities. So the very first postulate is regarding the state of a system. So postulate number 1. So this tells us about the state of a system. Alright, so what does this say? That all the information that is contained in a given quantum mechanical system is basically given to us by the solution of the Schrödinger equation, which is known as the wave function or the quantum state of that particular system. So the complete state, I'm going to be giving you notes, so if you are interested, you can note them down. The complete state of a quantum system, the complete state of a quantum system is given to us by the wave function So you can call it wave function, or you can also call it just a quantum state, or the ket or the ket vector psi. If you write it as a function, it might be a function of r and t, or you can have other representations as well. The complete state of a quantum system is given by the wave function, which contains all the information about the system. Which contains all the information about the system, right? And if you look at different textbooks may have a different number of postulates. So it doesn't really matter how many number of postulates there are. At the end of the day, the general idea is the same. So I'm going to be giving you 5 postulates which contain all the information. So one additional information that I want to include in the first postulate is that this wave function solution follows what is known as the superposition principle. This wave function solution follows the superposition principle. Now, this wave function or the state vector of a quantum system is not directly a measurable quantity. Like in physics, whenever we talk about a physical quantity, it can be measured, whether we talk about lengths, distances, velocity, electric field, or heat. We can measure those quantities. But in quantum mechanics, even though much of the theory surrounds the quantum state vector, we are not able to measure them directly. However, they contain certain kind of information about a particular system. So for example, if we look at a problem like an infinite potential well problem, where a particle is confined in one dimension between two very hard walls, then we can get a large number of solutions for that particular system, which we call as eigenfunction solutions. Eigenfunction means that they are orthogonal and they are normalized solutions of the Schrodinger equation. So depending upon the energy of the particle, which is confined between two walls, we can have a large number of, n number of, in fact sometimes infinite number of these eigenfunction solutions, which when we combine with the time dependent part becomes the wave function solution. The first information that we can gather from this kind of a scenario is something regarding the probability density of the particle. So whenever we are interested in finding out the region where the particle has a certain probability of existing, it is the psi mod square which gives us that particular information. And all the solutions of this particular system are differentiated by a quantum number n. A general solution for this kind of a system can be represented by a linear superposition of all these individual eigenfunction solutions. This is because the wave functions follow the superposition principle. That means if we have two solutions or more than two solutions, a linear sum of them is also a solution of the given quantum mechanical system. We can have a similar scenario in other kinds of quantum systems. So if we have a harmonic oscillator, which is essentially like a spring mechanism system. So in quantum systems, we may have two atoms which are bonded together, but the bond length is expanding and contracting. In that kind of a scenario also, we will get an n number of wave function solutions, where the general solution is a linear superposition of the n number of eigenfunction solutions. The same thing can be done for hydrogen atom, where based on the energy and the angular momentum, we can have a large number of wave function solutions for that particular system. So on one hand, we have the quantum mechanical state or the wave function solution that contains all the information about a particular system. But the second pillar of the quantum mechanical theory is something to do with operators, because it is the operator that extracts the information out of the quantum mechanical solution. So the postulate 2 is regarding observables and operators. Observables and operators. So as I just now said, that in quantum mechanics we don't really deal with various physical quantities directly the way we deal with them in other branches of physics. It is much more of an indirect approach. We have the quantum mechanical solution or the wave function, in which certain kinds of information are contained within it or stored in it, and we need to extract that information out. And to extract that information out, we have operators corresponding to various physical quantities, and those kinds of physical quantities are known as observables. So every single physically measurable quantity known as an observable is associated with a mathematical operator, which when it acts on the quantum state gives us some information about that physical quantity. Every physically measurable quantity, which is called an observable in the context of quantum mechanics, like position, momentum, energy, angular momentum, etc. Position, momentum, energy, etc. is represented by a Hermitian operator. So we have discussed Hermitian operators previously in one of my lectures. If you want to study Hermitian operators, you can look up that particular lecture. So it is represented by Hermitian operators acting on the wave function state. So for example, if I am interested in figuring out the energy of a certain kind of a system, so let's take the infinite potential well problem here. As I said, depending upon the energy of the particle in a box, it can have an n number of wave function solutions. Now, if I want to find out the energy associated with these wave function solutions, what I need to do is I need to apply the Hamiltonian onto the wave function solution. So if I apply the Hamiltonian onto the wave function solution, that will give us some information about the energy associated with a particular solution, which brings me to the third postulate. But keep in mind that energy is just one example. There are a large number of operators corresponding to different physical quantities, and the way to sort of make sense of the quantum mechanical theory is that these mathematical operators are tools that act on the wave function solution, and by doing that they give us some information about the physical system. So you can think of this operator as some sort of a machine through which the wave function passes through, and when it comes out of it we get some meaningful physical interpretation of the system. So now, based on this, how does an operator act on the quantum mechanical system? We have postulate number 3. Which is measurement and eigenvalues. So if the Hamiltonian operator acts on, let's suppose, a random eigenfunction solution of the infinite potential well problem, then this will give us an eigenvalue equation which contains the energy eigenvalue corresponding to that particular wave function solution. This is how the theory works. You have an n number of wave function solutions for a given physical system, and all these wave function solutions correspond to certain energy of the particle which is confined to the box. And when the Hamiltonian operator acts on one of the wave function solutions, then you end up getting an eigenvalue which corresponds to the energy of the particle which is in that particular state. You see, this is a very indirect way of actually getting something meaningful out of a given system, and thus revealing to us the structure of the quantum mechanical theory. That means the measurement of any observable and by observable I mean some kind of a physical quantity like position, momentum, energy, angular momentum, etc. The measurement of any observable, I'm going to call it as A. Okay, let's suppose A is a physically meaningful quantity or observable, is represented by the action of its operator is represented by the action of the operator or the mathematical tool corresponding to this physical quantity corresponding to the physical quantity or corresponding to the observable. So the observable is A, and the operator corresponding to A, I'm going to call this as A hat. A hat, okay? This is the mathematical operator. So the measurement of any observable is represented by the action of the operator corresponding to this observable onto the wave function state. The action of the operator on the wave function state. Let's call it psi, which yields an eigenvalue of the operator. So what is an eigenvalue? An eigenvalue is, quite simply put, one of the possible values of the physical quantity if we made a measurement on the system. So if we make a measurement on the infinite potential well, then one of the possible energy solutions will be the energy eigenvalue. Similarly for other quantities. So this is given by nothing but the A hat acting on a quantum state, and let's suppose its eigenvalue is given by small a times psi. Alright, this is a simple mathematical eigenvalue equation which contains within it the central core idea of the quantum mechanical theory, that you have a mathematical quantum mechanical state that contains all the information about a physical system. You have an operator associated with different kinds of physical quantities, and if this operator acts on this state, both of which are essentially mathematical in nature, it yields to us some kind of a meaningful eigenvalue corresponding to a physical quantity that we can then cross-check with respect to some sort of an observation. Which brings me to the nature of the final results, which in the context of this theory is inherently probabilistic in nature. So postulate number 4. Probabilistic outcome of measurements. Let's again take the example of the infinite potential well problem, where before measurement, before we probe the system to find out what is the energy of the system, before measurement, the system exists in n number of wave function solutions, right? The particle could have any energy, and therefore such a system is represented by a superposition of all the n possible wave function solutions, right? Now what happens if we actually do probe the system and try to find out the energy of the particle there? Then the wave function, which is a linear superposition of a large number of essentially eigenfunction solutions, will collapse into one of the possibilities. And the quantum mechanical theory can only offer us a probability associated with that particular collapse. So we can never really know before measurement the particle is in which state, but we can theoretically only give us a probability associated with finding a particle in one of the given states. So the fourth postulate therefore tells us that the probability of getting a particular result or getting a particular eigenvalue associated with one of the physical quantities can be obtained theoretically in this particular manner. So when we are measuring an observable, when measuring an observable or a physical quantity, of a system in state psi, let's suppose, the probability of obtaining one of the eigenvalues. So this kind of a eigenvalue equation gives us a large number of possibilities of measurement, but the probability associated with one particular measurement So the probability of obtaining one of the eigenvalues is given by the inner product of the generalized state and that particular wave function state mod squared. Probability of obtaining one of the eigenvalues corresponding to an eigenstate, let's suppose phi n. Okay, so here I have given you the eigenvalue equation in terms of psi, right? But if I want to specify it to, let's suppose we have n number of eigenstates, so let me call it as phi n, so that here I have phi n, and this is an. Okay, so basically an corresponds to phi n. So that is given by is phi n inner product with psi mod square for a normalized psi. Okay, so if psi itself is normalized, then the probability that if I made a measurement, then what is the probability associated with getting any one of the given states, right? So it's like throwing a dice. If you throw a dice, you don't really know which side or which face of the dice you are going to get, but there is a probability associated with the various faces, right? It's like tossing a coin. You don't really know if you're going to get heads or tails, but you do know the probability associated with getting heads or tails. Similarly, in quantum mechanics, whether you look at an infinite potential well problem, hydrogen atom, harmonic oscillator, or any kind of a quantum mechanical problem, you have an n number of eigenfunction solutions or wave function solutions for a given system. But there is a probability associated with making the measurement of a physical quantity corresponding to a given system. So it's possible that if you make a measurement of energy once, you might get a particular answer. Second time, you might get a different answer. And if you repeat the experiment n number of times, hundreds and thousands of times, you might get different results for similar systems, but you will end up getting something that is true based on the theory, which is a probability associated with getting a particular value. Now, these four postulates, they tell us an important idea in the quantum mechanical framework as to how the quantum mechanical framework works at a given point in time. You have the solution of the Schrodinger equation that gives us some information, but it's a mathematical information. You have operator corresponding to various physical quantities, but these are just mathematical tools. When this tool acts on the wave function solution, you end up getting some eigenvalue, which is some kind of a physically measurable quantity corresponding to a physical quantity. But what actually happens in the measurement, that is something that we can never really predict. What we can, however, predict is the probability associated with a certain particular measurement, right? So in this sense, the quantum mechanical theory is a probabilistic theory. Now, all these four postulates give us an idea about what is going to happen at a given point in time. What about the evolution of a system in time? So the fifth postulate tells us how this quantum mechanical state evolves with respect to time. So this is the fifth postulate with respect to time. It is time evolution. So the time evolution of a quantum mechanical system is governed by the time-dependent Schrodinger equation. The time evolution of a quantum mechanical solution or a wave function state let's call it psi t, is governed by the time-dependent Schrodinger equation. By the time-dependent Schrodinger equation. So if the Hamiltonian acts on this state psi, this is I h cross del upon del t on the state psi. This is the time-dependent Schrodinger equation, and the solution of this will give us an idea about the wave function state at a later point in time t. Now, I have done a video previously obtaining a very specific operator as a consequence of this equation, which will give us an idea about the time evolution of a state. So we can write that as well. So if you want, you can check out that previous video, where if you want to figure out the state at a later point in time t, then there is something called the time propagator e to the power minus iota Hamiltonian upon h cross t minus t naught acting on a state psi t naught. So if you have a state psi at t naught and you want to obtain how it evolves after certain time t, then this is the time evolution operator corresponding to it. So the fifth postulate tells us how a quantum mechanical state evolves in time. The second tells us about various operators. The third tells us about how the operators reveal to us certain eigenvalues corresponding to the physical quantity. And the fourth tells us about the probabilistic nature of the quantum mechanical theory itself. Together, postulate 1, 2, 3, 4 and 5 will give us a very formal presentation of the nature of the subject and how it is different from all other different branches of physics. If you study relativity, you should be familiar with the postulates of relativity, the two postulates of relativity. If you study mechanics, you should be familiar with the three laws given by Newton. If you study electromagnetic theory, you should know the Maxwell's equations. If you want to study thermodynamics, you should know the laws of thermodynamics. Similarly, if you want to study quantum mechanics, you should be familiar with at least the basic presentation of the main ideas in the quantum mechanical theory. I hope that you have understood this particular video, and having formally written down these various postulates will give you a new confidence as to understanding the formalism of this quantum mechanical theory. That's it for today. Thank you so much. I will see you in the next video.